This is elc138, worksheet 24, part B. And we did 1 through 5 the last time, so I'm at 6 and 7. And what's the capacitive reactance of a 470 capacitor at 60 hertz, 6000 hertz, and 6 megahertz? So what I did is I pulled up, this is chapter 4. This is the AC part of electric circuits. We've been using DC for most of the class. We're getting into some of the AC terminology, and so this is the formula we want to use. XC equals 1 over 2 pi times FC. Now if you remember what the inductive formula was, it was XL equals 2 pi FL, so there was no reciprocal. But in capacitive, there's a reciprocal. Most common mistake that people make is they don't put the denominator in parentheses and they enter the numbers in their calculator as 1 divided by 2 times pi times FC. You got to put that denominator in parentheses. So here's an example of a 100 hertz capacitor and what the reactance would be as the frequency changes. And what you see is as the frequency goes up, the reactance goes down. It's a reciprocal, and it happens to be opposite of what you see in an inductor. Okay, so I wanted to show you folks that, and I think if I go back, yeah, there's the master index. We did some stuff with complex numbers and inductance and now capacitance. And a little bit of basic AC theory probably has to do with the way things are going. So we'll get into some circuits in the AC class and transformers and all that, but I digress. So now I want to go back to 138.24. So what's the capacitive reactance? I just showed you the formula. I'm giving you 3 different frequencies, so as the frequency goes up, the capacitive reactance for a given capacitor should go down. And then I'm asking you to compare that to the inductive reactance, different formula, going up. And what you will see is that the inductance goes up and the capacitance goes down in terms of frequency. 1011. A circuit containing a series components of a 3 microfarad capacitor, 32 millihenry inductor, and a resistance of 400 ohms will have what impedance? What you will realize is your capacitive reactance is negative imaginary. Your inductive reactance is positive imaginary. And in a series circuit, if you have the ohms of capacitive reactance, inductive reactance, and the resistance, they're now all 3 vectors. The resistor vector points along the positive x-axis. The inductive vector points straight up, and the capacitive reactance vector points straight down, and it's a vector addition problem if they're in series. If they're in parallel, you would do the you would find their vector values, their capacitive, their reactances, and of course the resistance, you don't have to do anything, it's given. But these are now vectors, and to find out in a parallel circuit, it's the 1 over RP, except now it's 1 over ZP is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3. And you've got to respect the imaginary operator in the formula, because it does change things. So it's a little bit more difficult problem, but again, it is find the common denominator and then flip it at the end. There's your reactance, and everything should be good. And when you have reactive components and resistive components, you will get a mix. You will get an angle, or you will get an imaginary and a real part. What's the equivalent capacitance of a 40 microfarad capacitor in parallel with a 15 microfarad capacitor? I would go into that part of the book because there is a shortcut there. You could do them as reactances. You could do the parallel formula and do the flip, and what you do in then come out as reactance and then back up to what the capacitance would be. But there is a shortcut to that. What's the inductance of a 4.4 Henry inductor in parallel with a 0.2 Henry inductor? And what would be the equivalent inductance of the same two inductors in series? So I'm doing a parallel and a series. What you will see is that capacitance is funny, and it's going to actually be the opposite of the inductance. So parallel capacitors, you add their values. Series capacitors, you 1 over the capacitance value. In inductors, you add the inductors if they're in series, and in parallel, you would 1 over the inductance value. I don't stress that a whole lot because you don't use it a whole lot, but if you ever, it's a good little thing to know if you ever need a capacitor and you don't quite have the right size. You know how to get there. And 16, 17. If you need more help with 14 and 15, I'll be happy to work an example. Probably make another video. Just let me know. 16, 17. What I want to do. This is the last thing I really introduced in DC. Although some of my review problems, I think have a couple of concepts that you can have to look up that we haven't talked about. What period of time is necessary to capture 3 full waveforms of 60 Hertz waveform at 10 samples per one waveform? Okay, so I want to move in LT Spice to what we call transient analysis. So what we're going to do is we're going to set up the voltage source as a sine wave, and in the AC class we'll set up a square and triangle and all that. So 60 Hertz waveform, and normally when you sample a waveform, you sample at 10 samples per one cycle, or one wave. One complete cycle is what that should say. What should the sampling rate be? Well, I've got my handy dandy spreadsheet open, so if I've got a 60 Hertz frequency, and I want to know the period, it's equal to 1 over 60. So about 16.7 milliseconds is your period for a 60 cycle waveform. Okay, when you sample, you want to do about 1/10. But before you sample, let's round, because 1.67 is kind of hard to work with. So I'm going to say 0.17. There you go. 0.017. I'm just rounding to make things easier. And when I sample, generally when you sample a waveform in Spice or anything really, if you want a good representation of the waveform, you want to sample it 10 times per the period, or at 1/10 the period. You want 10 samples per period, or sample at 1/10 the period. So basically all you got to do is move the decimal. So 0.017 is your sample time. Okay, now I want 3 cycles. So one period is 0.017. What is 3 of them? Okay, so this is 1 cycle. I want 3, so I need 0.051. Okay, and that would be 3 cycles, and all I did was multiply. If I wanted 4 cycles, it would be 4 times this number. If I wanted 5 cycles, it would be 5 times that number. And we do this, we have to do this in Spice in order to get our analysis to, or transient analysis to look right. You really should do this ahead of time so you're not guessing. Whoops, I didn't get the extra 0 in there. There we go. Okay, I just added a 0. And I know that's 1/10. So there's 10 of these per every cycle. Okay, so this is going to wind up being my max time per step. Well, let me go to LT Spice and we'll set one up. Okay, I've put in a series resistor, inductor, capacitor circuit. I just did random. I want to go in and set up my DC source. I've got to go to advanced. And this is where I'm going to choose, it's a sine wave. And so when I do sine wave, I get all these different things I can add. Again, leave blank typically unless you know. So let's do a 10 volt amplitude. And this time I know my frequency. Those are usually the only two that you have to add. Number of cycles. When Spice does a calculation, you try and want to limit the number of cycles such that otherwise it's going to calculate forever. So you sort of want the number of cycles you want, maybe +1. So I wanted 3, so let's make this a 4 because that's +1. That's all I have to do. Give it my amplitude or my max, my VP. Give it my frequency. And now I have a voltage source here that will do a sine wave. Now I want to analyze it. You can't see what I'm doing, but I'm going to simulation. And I want to edit my simulation command. Okay. This will now make a little more sense in terms of the spreadsheet. Stop time. So, how long did I want to go if I want to capture 3 cycles? Well, we calculated it. 3 cycles is 0.051 seconds. And I'm pretty sure Spice will take milli if you want to, or you can just do 0.051. Time to start saving data is 0. Sometimes in AC circuits you don't want to start at 0. You want to start after 1 cycle. What you will see is a transient period where things are not at equilibrium. So in the AC class we're more interested in the equilibrium, or after things have come to a steady state. If you go on and become an electrical engineer, you will spend a lot of time in the transient period, what happens, and all that starting up, because the steady state then becomes trivial if you understand what's happening in the transient or the startup state. So let's do that. I want 3 cycles, and I asked for 4, so I think I'm okay with that. So let's add 17 to this, so that would be 68. And let's start after 1 cycle. So what I'm basically telling it to do is wait this amount of time before it starts showing me the waveform. That gives me some time for my transient to get out of the way. Start at 0 when you're starting out. But to get 3 cycles, the difference between my stop time and my start time has to be for 3 cycles. And my maximum time per step, that is my 1/10. So that's 0.0017. So I need those 3. I need to know my start time, which can be 0, my stop time, how far I want it to go, and my max time per step. And I like to calculate it up front because then I just have the values. So I click OK, and instead of a .op, I got this .tran in here. And now I can run my circuit. And this is how LT Spice shows us in an oscilloscope. Okay, I don't have anything on my waveform here until I probe. So I'm going to take my probe and I'm going to look at my voltage waveform, and you see I've got my 3 cycles. Now I told it to do 3 cycles, right? And you see where it went to 0 here at the 50 milliseconds? Well, I rounded and I rounded up. So if I would have had to tell Spice I wanted 4 cycles or 5 or whatever it was. Oh, I told it I wanted 4, and then I wanted the last 3. So if you don't tell it enough number of cycles, sometimes you get this at the end. But this is showing me 3 cycles. I did delay 1 cycle before it started saving data, so everything's at a value. So that would be my oscilloscope if I looked across the voltage source, and if I looked across the if I looked at the voltage on this side of the 10K resistor, I get a very, very small value. And if I look at the voltage across my capacitor, again I get a very different value. Let's go and get rid of that one, so you can hopefully see. There we go. Now the blue is the voltage right here, the red is the voltage right there, and what you see is my voltages are peaking and valleying at opposite places, and that's what tends to happen in an AC circuit. But that's beside the point. That is more than you need to answer the question, but it's where we want you to be at the end of the next semester in AC class, that you're comfortable doing this. So the more you experiment, do it up front, the better off you'll be. 138.24. Okay? So what period of time is necessary to catch your 3 full waveforms of a 60 Hertz waveform at 10 samples per 1 waveform? What should the sampling rate be, or max time per step, is what LT Spice tells you. And we calculated those. Okay? And then to analyze AC circuits, transient simulation command is used in LT Spice. This requires a start time, a time to start acquiring data, max time per step, using the answers from 16 to 17. The start time is 0, which is immediate. What would the stop time be and the max time per step be? I think you can do that. In a net list, the tran form is .tran, stop, start, max time per step. So what is your net list entry for tran 1819? So if you did it in LT Spice, you get that, but it wasn't what I asked for. So if I go in and edit my simulation command and say, okay, I want to start at 0 and only want to do 0.51, and I click OK, you see it changed my tran. And so that was the last question, because that's what it's doing. You can manually type that in, or you can go in and set it up. I always use the GUI to set it up. I think it's just easier. Okay, so that's pretty straightforward. Probably the most difficult are the equivalent capacitance of 40 and a 15 in series and in parallel, and the equivalent inductance of a 4 and a 2 in series and in parallel. But I believe you will find that in those 2 chapters. Okay? Alrighty. This is the end of worksheet 24. There'll be a couple concepts I cover in the review that are just look up. They should be fairly easy for you. I may change my review a little bit. Anyway, thank you for watching.